Okay, so we're going to start on lecture 6, data transfer instructions. With some announcements, which I already talked about, homeworks due today. We will first review some programming basics, assembly language programming, and then we're going to talk about the data transfer instructions. This is what we have talked about so far about x86 memory. It has 6 segment registers: code segment, stack segment, data segment, and we have 4 data segments: DS, ES, FS, GS, and each segment has 64 kilobytes and starts on a 16-byte boundary, which means that if you write the address of the segment, the last or the least significant hexadecimal digit will be a 0. In programs, in assembly language programs, the programmers care about logical address in a form as SBA and EA. SBA stands for segment base address, EA stands for effective address. And then we have some examples. DS colon SI, and in this case, the segment base address is in DS register and the effective address is in SI. The physical address of data is the actual memory address, which the processor will use to access the memory chip and to read or write the data. To get this physical address from a logical address, we need to do a little bit translation. The way we translate logical address is to shift the logical address, the segment register, to the left by 4 binary bits. And then we'll add the 16-bit effective address to the shifted result. And that will give you a 20-bit address, and that's the physical address. And sometimes we call it as a linear address, and in real mode, linear address is the physical address. To calculate the effective address, we have different ways to do that, depending on the addressing mode used by the instruction. Direct addressing mode, that's where you see a constant number inside the pair of brackets. And in that case, the effective address is the constant number, the value of it. The second case is so-called register indirect addressing mode. And in that case, what you will see in the instruction is a pair of brackets, and within the brackets you have one register. And the register could be SP, BP, or SI, DI, all these pointer registers or index registers. The only thing you want to be aware of for this register interact is that for BP and SP, you see these registers in bracket, and by default they have to be used with the segment-based register for the segment-based address. And the next one is the based index, where you have 2 elements, you want to add them together. One is the base register, and the other one is the index register. So for example, in this category, based index, you will probably see something like bracket BP plus SI. So this is the example of base register and index register. Then the next one is called register relative, where you're going to use 2 elements, 2 components. One is the register, the other one is the constant number. And the next one is the base relative plus index, where we have all these different options. You can have a base register and a index register and some constant value. And when you calculate the effective address, you just add them all together. The last one is scaled index. It will take a register and a scaling factor and multiply with the second register. So you will see 2 registers within the brackets, and also you will see a scaling factor in front of one of the registers. For x86 instructions, it can retrieve operands from two possible locations. One possibility is from a register, and the other possibility is from memory. For register-based operands, that's where you see the register name used inside an instruction, and you just access that register. And depending on the names of the register, you could be accessing an 8-bit value, or 16-bit value, or 32-bit value. So we have an example here. For register EAX, if we use AL or AH, that means we're going to access an 8-bit value, a byte. If we use name AX, that's a 16-bit value. And if we use EAX, that's a 32-bit value. To access data from memory, the data size usually matches register. If not, we're going to specify that explicitly using byte PDR or word PDR or dword PDR. Those are used in the case where the reading or writing to the memory, the data size is different from the register used in the same instruction. There are 4 general types of instructions used by most microprocessors: data transfer, arithmetic, logical, which includes shift, bitwise, and/or operations, and then program control. x86 has some additional types, which we may not cover in this class. For example, processor control. For example, you can have instructions to change the operation mode of the processor, or going into instruction interrupt service routine. And the other type is string instructions. This is where the microprocessor can process a stream of data within one instruction. Also, there are input and output instructions, which are designed to interact with devices mapped to I/O address space. We're going to look at data transfer instructions, and these are the few we're going to talk about in the lecture. Move sign extension, move 0 extension, exchange, load effective address, and load full pointer. And there are other additional data transfer instructions, and we will cover them in later lectures. For example, push and pop, those are the instructions specifically used for stack segment data transfers. And we have in and out instructions for I/O operations, and so on.
So what does LVA stand for?
Which one?
LVA.
Load effective address. Let's start with this move instruction, MOV. MOV is used to copy data between registers, or between registers and memory, or copy an immediate value to register or memory. And for the third case, because immediate value, that's actually just a number, and the number is encoded in the instruction itself, there's no storage space. So the immediate value can only be used as source operand. So it's going to copy from, so to copy the value to a register or to a memory location. The format of the move instruction is very simple. MOV space, D stands for destination operand, comma, S stands for source operand. And for the actual instruction, you're going to use either registers or memory operands to replace this S and D. The operation, the way we describe these operations is just by this parenthesis D equals parenthesis S. This is to say we're going to take the content of S and put into D. There's some restrictions on move instruction. For example, immediate value can only be used as source operand. And if segment register is destination, source must be memory or register. We'll see later in the example that because there's certain design artifacts that the x86 processors, if you want to copy a value to register, segment register, for example, DS, CS, you have to use another register, and most often we use AX to do this data transfer instead of using the immediate value directly. Let's look at this example. Assume we have these values in the following registers. We have 0100 in register AX, and we have 3000 in code segment register. And the next thing, what we say here is we have parenthesis DS colon 100H ending parenthesis equals 00H. What we're saying here is at that memory location, now the memory location is specified by this DS colon 100. Okay, see that's a logical address. Okay, and we use the pair of parentheses to indicate that we assume there's a value 00 in this memory location. We're not saying DS has value 00. We're not saying other locations. We're saying this DS column 100, this particular location in memory has a byte, and the byte value is 00. Similarly, this next location, DS column 101, and we have this byte, FF. So if I draw this memory, we have DS colon 100, DS colon 101. Both are hexadecimal numbers. In each location, we have a byte. And we have 00 at this memory location. And we have FF at the next location. Okay? So that's what we are trying to tell you in order to work on the next few examples. So let's look at the first instruction, move BL, AL. Which one is the source operand, which one is the destination operand? AL is the source, BL is the destination. And because AX has 0100, so we know AL is 00. And the destination of this instruction is BL. So we're going to copy the value of AL, which is 00, into BL. So BL will have the same value, 00. Second instruction, move DX, CS. CS is the source, DX is the destination. And we already know that CS has value 3000, and we're going to copy that value into DX. Yeah.
I just don't see why AL is 00.
Okay. So let's get back to the first instruction where we use AL, and because we already know AX has this value, and AX actually is made of A, H, and A, L. And AL is the lower half of AX. So that's why we know AL has 0, 0. Okay, the third instruction, move CX, comma, bracket 100H, ending bracket. So we know here we're going to do the data copy, and the source operand is a memory operand, okay, because of the bracket. That's why I know it's in memory. And the destination is CX. For the source operand, bracket 100, what is the logical address of that data? So the logical address is DS on 100. Okay. Because it's a direct addressing mode, we're going to take that number directly and use that as the effective address. And by default, the data segment is going to be used. That's why we have DS, and that's why we have this 100. The second question is, how many bytes we're going to copy from memory to CX? Bytes. 2 bytes, or 16 bits. How do we know that? Because the destination is CX, which is a 16-bit value, so we're going to copy 16-bit or 2 bytes from it. So now the question becomes, what is the value? What is the word in 2 bytes starting from DS 100? Okay, one of you said 00FF. There's only 2 possibilities, right? 00FF or FF00, depending on the endiness of the processor. And Intel processors use little endian, which means that the most significant byte is at higher address, and this 00 is the least significant byte. So if we're loading this word into CX, we're going to use FF as the MSB and 00 as the LSB. So that's going to be FF00 loaded into CX. Any questions?
Within the byte, does it matter which letter or number comes first?
Good question. The minimal addressable unit for the memory is a byte. So whatever 2 hexadecimal digits here, that's going to be the same. There's no additional endiness within a byte. Okay, now we have a longer program. We have 10, 11 instructions, and these instructions are used to initialize internal registers with some initial data, immediate data. Okay, I'm going to give you a couple of minutes to work on this, and you can tell me what will be the final values in all these registers effective. Okay, let's work on these instructions. So all these are data copy instructions or data transfer instructions. Starting from the first, MOVAX, comma 2000 hexadecimal. So that's just copy an immediate value into AX. So now AX has 2000. So these red fonts on the right indicates the values in those registers after the instruction is completed. Next instruction is move ds comma AX. We said earlier that these ds is a segment-based register. We can only do these data transfer using another register. So that's why we have these two instructions instead of having a move ds comma 2000. So after the second instruction, ds also has 2000. The third one is similar. We put the value 2000 into ES. The fourth instruction, now we have a new value in AX. Okay? After this fourth instruction is completed, AX has value 3000. And we use that value to initialize stack segment. That's what we do in the fifth instruction, move SS comma AX. As a result, SS has the same value, 3000. The sixth instruction, move AX comma 0H. So we're gonna put a 0 into AX, and following that, we move BX comma AX. As a result, BX has the same value, 0. And the next one is move CX comma 0AH. So we're going to put value 0A into CX. And the next instruction is move DX comma 100H. So we're going to put 100H into DX. And the last two instructions are used to initialize those index registers. So as a result, SI has the value 0200 and DI has the value 0300. So, okay. Now, sometimes we say 0200 or 200. It's the same number. When you add 0 at the beginning, it's the same number. And the reason we put 0200 for that SI is just to indicate that's a 16 value, so you have 4 hexadecimal digits, but it's the same number.
When do you immediately move a number to a destination, and when do you have to initialize it?
So other than doing these segment registers, you can copy the immediate value into registers or memory. The only exception is the segment-based registers, ES, CS. Okay, now we're going to look at two similar move instructions, but with some slight caveats or some extra operations. These two instructions, MOVSX and MOVZX, they're going to do two things. First, they're going to do the move or copy, and then additionally, they're going to extend the data. By extending the data, we mean it's going to fill upper bits with zeros or ones, depending on which instruction you use and depending on the actual value you copy to. ZX is 0 extension, SX is sign extension. For the sign extension, you're going to copy the MSB, sign bit of the number, into the source. The format is similar to the plain move instruction. Now we have MOVZX, D stands for destination, comma, S. And then we have MOVSX, destination, comma, source. The operation is, as I said, including two steps. First is data copy. It's going to copy the destination, lower bits of destination. Calculate the source into the lower bits of destination. The second step is to do the extension on the upper bits of the destination. For MOVZX, that's going to be putting zeros on the upper bits. For MOVSX, that's going to be depending on the MSB of the source. Some restrictions only register memory operands. There's no immediate values can be used for either source or destination. The source must contain fewer bits than the destination, and if memory operand is used, size must be specified.
So if you use most zero stand, we put zero in the place.
Can you see that?
If
Okay.
you use most zero stand,
Mm-hmm.
we put zero on the left of
The destination, yes.
the
So we're going to look at a few examples. We assume AX has 0100, DX has 8100. And again, we assume we have 00 in memory location DS100, and we have a byte FF in DS101. What are the results of the following instructions? So we have 5 instructions, 3 are sign extension, 1 is 0 extension. And I would like to give you 1 minute to work on these 5 examples. Alright, so let's look at what's going to happen after these instructions are executed. First instruction, move sign extension EBX AX. So let's first look at what is the source, what is the destination. AX is the source, EBX is the destination. And the restrictions on these source and destination operands for sign extension move is that source must have smaller number of bytes than the destination, because that's how we can do the extension. And the goal is to use the value of source and to fill out the destination, which has more bytes than the source. And AX has 2 bytes, EBX has 4 bytes. So we do have a way to do the extension. In AX, we know we have a value 0, 1, 0, 0, and if we look at the sign bits is 0. The most significant bit of AX is 0. So we're going to extend by filling zeros to the upper 2 bytes of EBX. So the EBX is going to be the destination, and the lower half, the lower 2 bytes, going to have the same value as the AX. and the upper 2 bytes is going to have all zeros because we're extending the sign bit of AX. So, okay, so we're doing this sign extension, okay, and AX is the source operand. So we're going to look at the value of AX, and the value of AX is 0100 in hexadecimal. And if you write this number in binary, you will see you have 0000, 0001, and then 000, and then 000. So the most significant bit of AX is its sign bit, which is a 0. And we're going to extend that sign into the upper half of EBX. So the most important thing is, first you need to figure out what is the sign bit of the source operand, whether it's 0 or a 1. If it is 0, then we're going to fill up zeros on the top. Next instruction is do the sign extension, and the source operand is a DX. And for DX, okay, what is the sign bit? Is the sign bit 8? No. When we say sign bit, we're talking about a binary bit. So we'll have to write this number in binary. So you can see this 8 becomes 1000. And so the sign bit is a 1. That is why when we do the sign extension, you see the upper half of the destination, EBX, is all filled with 1. But in fact, after the sign extension, this 32-bit value has the same numerical value as the source. It's a negative number, and you can figure out what is the actual value of the negative number. Third instruction is MOVZX, that's 0 extension, EBX, comma, DX. Now this is a clear comparison with the previous instruction. So even though DX again has 1 on the sign bit, we're gonna ignore that. We're gonna put in all zeros on the upper 2 bytes of EBX because this is 0 extension. Yeah, so you have all zeros on the upper half of EBX. Next instruction is move sign extension EBX, comma, byte pointer bracket 100. Because of the byte pointer bracket 100, we know that we are going to retrieve the byte, well, the source operand, which is a byte from memory. And the memory location is DS100H. Okay? And that value is 00. So we're going to extend this byte 00, and we're going to do the sign extension because 00 is a 0, the sign bit is a 0, so we're going to extend that, and so that's why you see the upper 3 bytes or the upper 24 bits are all zeros. The next instruction, now we change byte to word. So we're going to do the word pointer bracket 100H. So this now is my source operand. And from the previous example, we know that this, if we retrieve a word from DS colon 100, which consists of 2 bytes, 00 and FF, the word will be FF00. Okay, let me explain this again. We're going to look at this source operand, which is word pointer 100H. So we're gonna retrieve a word from DS colon 100. Okay, the DS is because the default data segment, and the 100 is the effective address. And I just erased the diagram, but if you remember, we have FF00, that's the word we will get using DS100 as the address. And then, because FF00 has a 1 on the sign bit, and we're going to extend that on the upper 2 bytes, or 16 bits of EBX. The upper half of EBX are all 1s. Any questions? Right, so that's all for lecture 6.